Good morning, good afternoon, good evening to all the attendees to this talk that will be done by Rob Aitken from ARM Research in San Jose, California, USA. California. So thank you again for accepting our invitation. So the talk will be about the challenge of software-defined hardware. And Rob Aitken is an ARM Fellow and Director of Technology for ARM Research. So responsibilities include developing ARM's research agenda, include identifying disruptive technologies, monitoring the global technology landscape, and coordinating research efforts within and outside of ARM. He has served as General Chair and Program Chair of the Design Automation Conference and International Test Conference. And he has published over 100 technical papers on a wide range of topics and holds over 40 USA patents. He holds a PhD from McGill University in Canada, and Dr. Aitken is also an IEEE fellow. So thank you again. We know that you have a lot of achievements in the field, so it's a great honor for all us to have your talk today. So now the floor is with you, Rob.
All right. Thank you very much, Ricardo. And today's talk is on the challenges of software-defined hardware. Part of it will be explaining what exactly I mean by that. I'd also like to acknowledge a variety of people, current and former colleagues at ARM Research who helped with ideas, material, thoughts, and so on around this talk. We need to start out with what is our definition of software-defined hardware? What do we actually mean? And what I'm saying is we mean that a vision of programs that are able to self-identify the own ideal hardware for them, map themselves to it, and execute seamlessly. So if we imagine a block of code like the one on the left there, it's able to identify chunks of itself that make sense to run on a CPU, chunks that make sense to run on a GPU, chunks that make sense to run on some kind of a neural processor or other accelerator. All of that happens seamlessly and it happens dynamically. So that's really the vision of software-defined hardware that's proven quite challenging to achieve, and we'll look at some of that. The first and most obvious statement is that software isn't really like hardware. And so we have a challenge of mapping software concepts onto hardware and vice versa. Among the differences, software is inexpensive to develop. It's expensive to maintain. Hardware is kind of the other way around. It's very expensive to produce a chip, but once you've made a chip, you don't really have to do a whole lot to maintain it. If you compile software, in a few minutes you have a new version. If it takes 20 minutes, you become frustrated. On the other hand, with hardware, once you tape it out, then you've got a 6-month or so wait until you get silicon back. If your software has a bug, you patch it. If your hardware has a bug, you have to respin and spend another 6 months making some more chips. There's another important difference that leads to a kind of a mindset change, which is that once I have some software, I can make copies of it effectively for free. It's not exactly free, but it's close enough. And all of the copies are effectively the same. And again, there's subtlety there, but to a first approximation, copies are free and identical. Whereas for chips, the copies cost money. You have to build each of them, and they're not identical. That there are variability and defects and so on, which again is a topic for another day, but it underlies kind of the apples and oranges discussion that when you're comparing hardware and software, they're not the same thing. Another piece that we have to think about with hardware and software is everything in technology is in some way related to Moore's law. It's the elephant in the room, the unstated presence, whatever you want to call it. And effectively, because we've been at this for 56 years, since the publication of Moore's original paper, everyone working in this field has worked either their entire career or the vast, vast majority of their career with some aspect of Moore's law in the background. And the key point for today's discussion is that Moore's law is really about expectations. And the expectation that's the most important is that there will be an ongoing, everlasting progression of improvements. Everything gets better all the time. So you expect your next phone to be better than your last phone. You expect the one after that to be better, and so on. And even though we might not think about it all the time, this expectation really underlies a lot of our work. And I'll show you why here in a minute. So if we take a look at, these are two figures from Moore's original paper. And we're used to the one on the right, but the one on the left is equally important. So let's take a look at what I mean. So we're used to the one on the right, which just says that every year to 18 months to 2 years, effectively the amount of devices that you can put onto an integrated circuit doubles. So since Moore's original trend starts there in 1959, between 1959 and now, there have been a total of 36 doublings. So we've gone from 2 to the 0 transistors to 2 to the 36th, kind of the 50 or 60 billion range of transistors on a logic chip. That's close to a 50% cumulative annual growth rate for 62 years, which again is very impressive achievement. The figure on the left, though, is important as well. So that what it shows is the optimal point, the optimal density point. So as you move from one technology to another, it's not just that you can put more circuits onto a chip, but you can put more circuits onto a chip more cheaply than you can put fewer circuits. The optimal cost point is really what this graph charts. And even in 1965 or 64, Moore was pointing out that there's a way to increase device count that actually makes cost worse. So that's the red arrow there. And a lot of what's being offered now as this is a Moore's law extension really isn't. It's an increase in density that comes at an increased cost. So that's the red curve on Moore's law, and or the Moore's graph, and that's not technically Moore's law. So again, hold that thought. It becomes important as we go forward. So we've seen 56 plus years of growth, but now we're seeing demand for compute slowing down. What does that mean? What does it mean? The compute capabilities are slowing down, but the demand isn't. So let's take a look at natural language processing. So in February last year, Microsoft announced the 17 billion parameter model. So wow, that's pretty exciting, 17 billion. Meanwhile, 5 months later, another model was announced with 175 billion. So this is 10 times as many parameters. It took 5,000 petaflop per second days of effort. Now, if petaflop per second days is sort of a weird metric. It's kind of like miles per hour hours. It effectively cancels out the time component, but what it corresponds to is a petaflop per second day is around 10 to the 20th operations. So a huge number of operations. It took 5,000 times that to train this model. Then shortly after that, in early this year, Google trained a trillion parameter AI language model. So Moore's law talks about doubling every 18 months. What we're seeing here is 17 billion to 175 billion to 1 trillion in less than a year. So that's a 50x change in less than a year. So demand for compute is not slowing down, and yet at the same time, the ability of hardware to keep up is slowing down. So going back to the idea of software-defined hardware, we've been at this idea for a while. So here's an early effort. This was a silicon compiler that was published by Dave Johansen et al. Back in 1979. The idea was automatically constructed hardware. And a quote from early in the paper says, "What if a person were able to sit down and design a computer chip in a single afternoon?" Well, that's really pointing at this software-defined hardware goal that we've been talking about. They used that, they set up a company, Silicon Compilers Inc., and they actually used their techniques to develop the data path chip for the Microvax computer. And they designed that in 7 months, which was back in 1983, a reasonably good time period. The thing on the left is the Microfax, the thing on the right is a printer. Both of these things you can see are physically large objects. The performance of a Raspberry Pi is about 2,000 times greater than the performance of that microvac. So again, you can see Moore's law in action just in terms of what was a state-of-the-art mini computer in 1983 versus what's a toy that you can play with now. To also put things in perspective, remember that model that took 5,000 petaflop second days to train? If you'd set the microvacs doing that at the time of the Big Bang, it would just be finishing up right about now. So 10 billion years worth of compute would have been about where we got to. All right, so software-defined hardware, we've been thinking about it for 40 plus years. We've been trying various techniques. Why doesn't it exist? You'd think it would exist by now. And I'll suggest there are 3 reasons why it doesn't exist. Number one is we keep wanting more, and we'll talk about that. Also, we don't really know what we want. And thirdly, what we really want might actually be impossible. So when I was thinking about that last point, the last 2 points, I was thinking about this verse that came out on a parody of the "'Twas the Night Before Christmas" song that originated again back in the dark ages of the internet. But the last line of the poem is, "And the user exclaimed with a sneer and a taunt, 'It's just what I asked for, but not what I want.'" And that's a sentiment that we're all familiar with in the technology industry, is that we think we want something, then we go and build it and discover that that wasn't quite what we wanted. We wanted something else. And software-defined hardware falls into that, I think. But first, let's look at more. We want more, but more is never enough. And the builders of freeways have observed this over time. You keep adding more and more lanes to a freeway. You would think that if you added more lanes to this freeway, that traffic would go down. But it actually doesn't. Traffic often stays the same or even goes up, because now that there's a bigger freeway, people re-optimize their decisions and they decide to drive further, because they were optimizing their decision on travel time. And if you make the freeway easier to drive on, it just means that you can go on longer trips. And as a result, more people are on the freeway and traffic just stays where it was at. So again, we want more, but more isn't enough. But we still want more, even though it's not enough. But what does that actually mean? Do we actually know what we want? So we want more of something, but what is it that we want more of? Do we know? And I'd postulate that not really. We really are not entirely sure what we want. So let's look some more at what that might be. Joe Jackson back in the 80s had a pop song called "You Can't Get What You Want Until You Know What You Want," which again is a statement of the obvious, and apologies for using obscure British pop to make a point. But the idea, I think, is a good one, that if we don't really know what we want, we're unlikely to notice if we get it. So it's important that we know something about what we want. One angle that we've looked at over time is high-level synthesis, and that there was sort of a joke. Marilyn Wolfe made this in her panel at DAC last year. It's the meteoric rise of a hot topic. 1974 and onward. So academic work in the high-level synthesis has started in the 70s. Behavioral compiler, synthesizer, System C, System Verilog, all these things showed up somewhere between 20 and 25 years ago. So we have now a functioning high-level synthesis ecosystem. Do the tools work? Yes. Are they software-defined hardware? No, they're not. And that's interesting. So why are they not? I think there's 2 main reasons. Number one is the partitioning of the problem that they do is static. You take your algorithm, you pick some piece of it, you say, okay, I'm going to implement this piece of it with an ALU, I'm going to implement this other piece of it with some other functionality. And it's really a hardware-centric approach. It's an idea of how do I write in a software-looking fashion, something that looks kind of like a programming language, something that's actually more of a hardware descriptor language. So we've effectively realized that we didn't quite know what we wanted. So we didn't want a static partitioning hardware-centric approach. Instead, we wanted some kind of a dynamic software-centered approach. So a refinement on what we've known or what we want means that we're now looking for something slightly different. Around this point in the talk, it's important to have our obligatory machine learning discussion. The reason for that is that ML really is today's canonical workload. It's everywhere. So I just pulled this one up. There's a site called Machine Learning for Kids, and it's actually a pretty good site. It gives you ideas for in classroom materials to train children and how to program machine learning. So here's one that's called Make Me Happy, and it essentially does some sentiment analysis and some supervised learning to train this little face to smile or frown depending on whether it receives a compliment or an insult. So machine learning is everywhere. Not only that, it's expandable. And what I mean by that is with a trillion parameter natural language model, that can only exist in a data center. But on the other hand, something like keyword spotting, the thing where you say, hey, machine, where's my coffee? That level of understanding is very primitive, and that will actually fit on a very, very simple microcontroller. So everywhere in this universe, from tiny microcontrollers up to dedicated data centers, is a place where you can put machine learning. The last point about it is that it is still an unsolved problem, where there's still lots of work being done, great advances being made on it literally daily. Here's an example of a piece that's not solved. I have this project at my house, which I've just taken a security camera and I run it through machine learning, and its job is to identify people. Now, any particular model has some inaccuracy. This one is using MobileNet. It was trained on Cocoa. It has 90-something% accuracy in people identification. But unfortunately, there's a correlation issue that comes up. So it misidentifies this particular lamp as a person. And it does it over and over and over again. In fact, it does it so much that eventually I'm going to have to retrain this, or somebody else suggested YOLO v3 instead of MobileNet, so maybe I'll try that. But in any case, the point is that once it makes a mistake, it just keeps on making it. You might argue that 27% really isn't that big a deal. Here's another one that identifies as a person with much higher probability. I'm not entirely sure how this thing is a person. It looks, maybe it's like kind of a strange snowman. But in any case, machine learning remains an unsolved problem. However, again, big progress has been made. So this is the ARM platform, but similar ones exist for other technologies as well. Effectively, what you have is you have people writing their high-level frameworks. So the kids doing their ML, or people doing more, commercial programs or whatever. They're writing in things. They're writing in PyTorch, or they're writing in Caffe or TensorFlow. Then there's a code generation piece of it, which is based on TVM, which is a compiling tool. And then that goes in turn and redirects itself down to whatever it is that's the hardware target. So in this case, the hardware targets span high-performance CPUs, microcontrollers, neural processors, GPUs, and etc. This capability exists, so we can take code generation and we can map it to multiple targets. So is that software-defined hardware? And the answer is no, that's not really software-defined hardware either, but it is kind of software support for existing hardware. So again, bits and pieces of the software-defined hardware problem have been solved or in the process of being solved better, but nonetheless, we're still not quite there. There's a DARPA program in the US that's based on this. So it's even called software-defined hardware. The goal for that program is to get within 10x of ASIC level performance while retaining programmability. So in other words, if I built a custom piece of hardware that solved a particular problem and only solved that problem, I want to be able to get within 10x of that while retaining some level of programmability. And the diagram on the right comes from that program, and you can see there's really two pieces for it. There's the reconfigurable processors part, and then above it, there's a compiler part that says, let's dynamically adjust the hardware that we're targeting this to based on what's happening with the data right now. So is this a sparse matrix? How sparse is it? Should it go to this accelerator, that accelerator, and so on? ARM is participating in this program. University of Michigan is actually leading the team along with Edinburgh and Arizona State. The results so far look pretty good. So, you know, this is making progress, but where are we at? The reason, though, that I think we can even think about this comes from this idea of dark silicon. So the idea, this literally is a slide from at least 2008 that I'm repurposing here. And what you see here is that in 2008, the idea was we have some sort of thing that's taking up a die, and it does something. It has some area, frequency, and power. If we scale that at the time using ITRS methods to the 22 nanometer node, a couple of nodes in the future, the area quadruples. The peak frequency does not quadruple. It only goes up by a factor of 1.6 or so, and the power stays the same. And there's lots of reasons behind this, which we don't need to go into. But effectively what this means is that if you have an ISO power budget, that you're limited to effectively 25% of the die. And the rest of it, you're not doing anything with. And similarly, if you extrapolate that to the 11 nanometer was the predicted node. 11 nanometer actually never turned out to exist, but nonetheless, then you're down to, again, 10% of the die is exploitable. So this was the vision in 2008. So this was going to happen. When it happened, there would be a whole bunch of hardware space that you weren't able to use for anything. And essentially the reason why this has relevance to the software-defined hardware problem is that the idea was that if you only can use 10% of the die at any given point, that means that you could actually have 10 different pieces of hardware that did 10 slightly different things, and you could just turn on the one that mattered whenever you needed it. So that was the idea in 2008. What happened? If you look at what actually happened, up to current time frame, I haven't updated this for 7 or for 5, but at 7 nanometer, again, we can see that it followed pretty much the trajectory that was predicted. FinFETs gave a little bit of a boost when they showed up, but we're still at basically these dimensions and frequency and power numbers that were predicted in 2020 or in 2008. So dark silicon as a technology trend really did happen. The technology trend is real. So we're now sort of 12 years into this trend. What came of it? What happened? So one thing to look at is, let's take a look at smartphones. So in smartphones, prior to 2008, cell phones had all had effectively the same power consumption. And the power consumption wasn't really limited by the battery so much as limited by the heat dissipation of the phone itself. And phones kept getting smaller, so that requirement went down. Since 2008, however, with the introduction of smartphones versus conventional cell phones, the screen size started increasing. And then when the screen size increases, you get more heat dissipation, and you also get a place to put a bigger battery. So the battery capacity increased. And as a result of that, the CPU power is increased as well. And you can actually see that in this graph here, which shows data from AnandTech on apples to apples similar cell phone processors moving forward in time. And you can see at 90 nanometer, it was kind of around 500 milliwatts. But by the time it gets to 7 nanometers, it's close to 3,000 milliwatts or 3 watts. So the maximum CPU power has gone up quite a bit. Well, what else happened? In data center, the power did not go up. Instead, what's happened is that the energy usage has actually stayed fairly constant. And again, there's a lot of details in this in the science paper, but what you can see is that even though the amount and demand for compute went up, the actual efficiency of providing that compute also improved, and that the net effect has been to kind of balance. So even though a few years ago there were these predictions that the amount of energy consumed by data centers would take over the universe, it didn't really happen. Instead, what happened was that there's more and more compute happening in data centers, but they're becoming increasingly power efficient, so that the net effect is effectively constant. Another thing that's happened is that a lot of the design techniques that we were talking about as sort of innovative and new back in the mid-2000s, power gating, power islands, voltage scaling, et cetera, those things went from new and interesting and maybe, risky to just ubiquitous. Everybody is using these things everywhere. We're also seeing the increased use of special purpose compute engines. And that was really what the dark silicon predicted, the idea that there would be an opportunity to have GPUs, neural processors, things that you didn't use all the time, customized processing capability, but which was available when you needed it, and the rest of the time could just be turned off. So this is essentially what that means is that the vision that was worried about this crisis in dark silicon actually turned out to happen and be used. And what happened to that crisis? Was it a crisis? This cartoon is actually originally from 1974, and it was related to one of the early energy crises in the U.S. But I think the point that it makes is important. Effectively, the idea is that if you have a crisis and you exist with a crisis for a long time, then the crisis really isn't urgent, or it's not a crisis anymore. It's effectively just the status quo. And because it's the status quo, it's no longer a crisis. Therefore, the crisis has ended. And that's, in the cartoon, the politician is looking to take some credit for that. But in terms of dark silicon, this worry that suddenly we weren't going to be able to do anything with our chips actually turned into an opportunity to produce a bunch of hardware that was very specialized, multi-purpose, and be able to turn that on and off as needed. That has resulted in a kind of moving the goalposts phenomenon. And what I mean by that is, if you take a look at chips are expensive to build. And because they're expensive to build, there's an expectation that they should be hard. So in practice, that means that I could take a 1980s era chip, the kind that was being originally thought about in the Silicon Compilers paper, and I could design that in an afternoon. So could you, any of us could. But wouldn't it be better, if we're going to spend a lot of money, not to just design a chip in an afternoon, but to spend a few months designing a better one? And that's kind of where we've got to. We've moved the goalposts in terms of what hardware design looks like. And that in turn has changed our expectations for what software-defined hardware means. Which then brings us to, is software-defined hardware possible at all? And as with so many questions in technology, the answer is, it depends. So we can do difficult things immediately. If they're impossible, it just takes a little bit of time. To explain why, let's take a brief diversion back. Again, going back, this is my excellent AI adventure in the 80s. So I was working at a place called the Alberta Research Council in Canada. The group of people sitting up there on that mountainside in the top right, those are kind of a good chunk of the AI brainpower in Canada in the 1980s. Of those people, I think the only one still really working in AI is Sheila McElraith, and she's a professor at University of Toronto who's very big in the AI world. But the rest of us have all kind of gone on and done other things. But the point, rather than just reminiscing and showing you funny photos from the 80s, is what we were working on, or what I specifically was working on there, was this expert system. And the particular expert system that I was looking at was related to this Mycin thing that's over there, or on the right. And effectively what it did was it took a bunch of symptom data and merged that with a bunch of expert views on what those symptoms might entail. So there's a quote here from a Harvard Business Review around the same time, that they're going to make machines achieve human-like capabilities such as seeing, hearing, and thinking, and expert systems are a subset that lets you solve tough problems like freight scheduling, contract estimation, etc. So that was the kind of the hype around it. And the idea was that we're looking at this AI, and this expert system is meant to be something like artificial intelligence. But it really isn't. The The shortcoming of expert systems is they can't actually generate anything new. Instead, they can allow you to interpolate things that are already known, so that they're able to augment human decision capability, but they aren't really able to replace it. So they're not really artificial intelligence. And that was kind of the realization that I came to back then working on it. Whatever artificial intelligence is, it isn't this. So does software-defined hardware, do we have to solve the general AI problem to solve that? And I think we do in some formulations. So we need to, because we're not likely to solve general AI anytime soon, we need to kind of rethink how we come apart or we approach this problem. A first key challenge in that space is incorporating designer intent. The designer wants something to happen. Whoever wrote the program has some anticipated understanding of how it works. We need to be able to extract that, and what precisely that means is actually quite a challenging problem. Secondly, we need to be able to take, because these chips are expensive, we need to be able to maximize what they do. So whatever it is that they're up to, it should be done well so that we can justify the expense of creating one of these things. Again, because chips are expensive, we want to reduce the number of specific designs. If we have 1,000 different programs, it would be better to have a few chips that are able to handle all the programs, rather than each of the 1,000 programs requires its own chip. We also want to be able to respond dynamically to data. And there's two aspects of that. One is the part that I talked about already. We want to be able to take problems that have varying degrees of sparseness, and we want to be able to move around in between them. But more broadly, we want to be able to say, if this class of data or if this type of data changes, if we get more of it, if we get different kinds of it, if we come across different ways of thinking about it, we want to be able to respond dynamically to that. So we want to be able to change our algorithms as well. And that's kind of the adaptable to the future piece of it. If you build a chip and then you have to wait 6 months for it, and in the meantime, the algorithms have moved on and that particular design is no longer of any use, you really haven't solved any problem at all. So given this situation, what's ahead? Where are we going in all this stuff? So one place that we need to work is software needs to be written to be hardware aware. And parallel structure is really a key in that. Some of this can be identified by clever compilers or by programming languages that favor structuring things this way. But there's still a problem of how do we identify inherent parallelism? Is there a way for programmers to give us hints when they know it's there? We also want to understand the underlying trade-offs. And so this is really from an intuitive level, that there's a speed versus flexibility trade-off. The more flexible and programmable I want something, the slower it's going to be. A general purpose CPU is not nearly as fast as a dedicated piece of hardware that runs one single computation. There's another trade-off that's a little bit more subtle and kind of an optimization versus ubiquity thing, which is that if there's a function that everybody on the planet uses, we can design a really hyper-optimized piece of hardware for that specific function. On the other hand, if there's a function that's only used once, there really isn't justification to spend that much effort optimizing it. So there's a library trade-off. In programming, it's analogous to if you have a Python library for something like machine vision that's exceedingly common these days, it can be really hyper-optimized below the surface. Whereas if you're trying to do some other computation on topology or something that people rarely do, it's unlikely that underlying structure has been optimized particularly well. So again, we want to have compilers and libraries. They have to be able to find hardware connections. So we have to be able to, going through a piece of software, whatever language it's written in, we need to be able to find places that map nicely to this hardware. And there's been a lot of progress in this area, but there's still lots of work to be done. Once we get something, the implementation needs to be affordable. And that's, again, there's a lot of work behind this. Some of the open road stuff, for example, fits into this piece. There's just a general need, though, for whatever pops out of our software-defined hardware, whatever that top-level hardware structure is, turning that into working silicon has to be fairly straightforward, and it has to include fixing problems at multiple layers along the way. And the beyond RTL parts of the design just need to work. And so there's huge numbers of these things. When you think about, well, I've just written this code, there's all sorts of other stuff that gets layered on top of it. Some of it gets written up in the RTL or as as side files, things like power definitions. The security properties of the system need to be thought about. That's, again, its topic in itself. Testability, sign off, and all the rest. All these things are really important, and they all need to just work. And the last piece that's worth considering is that if we're doing this now, then whatever target hardware object we have is more likely to be a package than just a single piece of silicon. So let's think about that. As I was preparing this talk, this article came out, and I wanted to include it. So this is by Thompson and Spanath in last month's communications of the ACM. So the title of the article is Decline of Computers as a General Purpose Technology. And the article really goes, you should read the article, but it goes into great depth about how slowing Moore's law increases justification for specialized processing. So essentially, you've got this idea of slow technology advances, and that, let's back up. On the left-hand side, technology advances quickly, so that encourages more users to join the system, which provides more financing, which creates this virtuous circle. And what they're arguing is that at the moment we have the opposite, where technology advances are slow, that causes users to leave, which then causes reduced financing, which then breaks the system effectively. So is that what's really happening? And when you hear news items on things like worldwide chip shortages and so on, you know that it's not quite what's happening. And so I'll suggest that what's happening in technology is more like this. So technology advances are becoming increasingly expensive. Next generation fabs are billions upon billions of dollars. And what that means is that fewer users can afford to pay. So not that there are a few users who want to play, it's just that fewer users can afford it. That in turn means that the big players will still get what they want. And in turn, the innovation that's financed is going to be more targeted. So it's going to be more directed to the specific problems that those big players want solved. And in a way, that goes back to the same thesis of decline of computers as a general purpose technology that in the article, but it's slightly subtle variant on it. So the big players are going to get what they want. Others are going to have to play a different game. And that means that they're going to need a new approach. And I think we're going to see what that means play out. We're already seeing some of it in terms of who can afford to be at 7 nanometer or 5 nanometer or 3 nanometer versus who's just going to continue to play at 28 or even 180. If you look at foundry revenue over time, a big chunk of money is still made at 180. That brings us to what we actually are going to have to look at. What is this new game going to look like? And I think it's going to look like we're going to have to go beyond incrementalism. So we can't just do port previous design to new project process tweaks. Dennard scaling will deliver big gains. That is out of gas at this point. We're going to have to look for something new, either new algorithms, new circuits, or a fundamental rethink of the underlying structures. That means that, again, we're going to have to devote time and effort to make them work. And that means, again, that but a benefit of slower scaling is that we have this time. So and again, there's a subtle thing in that too. If you look at the actual Moore's Law generations over the last few years of going from first FinFET node to 10 nanometer to 7 to 5 to 3, they're on a pretty rapid cadence. So the cadence hasn't really changed that much. But what has changed is that the actual feature changes has slowed down quite a bit, which means that you have some time. If in the 90s, if you had a new idea, you didn't really have the time to implement it because the next node was coming so fast, you only really had time to port to it. Now you do have time to think about it, and that means that we can actually spend some time to come up with some new approaches. Let's take a look at some of those, what approaches are. There's the chiplet idea, where we're just going to stack a bunch of things together, and there's the 2013 view of that, where let's stack a whole pile of things up and make super chips. Or the more recent version of it, where let's get a bunch of tiny silicon blocks and glue them together. I think that's on the right track, but I don't think we're going there yet. Instead, I think we're going to go to something that's more like this, where you've got this idea of just simple die stacking. We'll call it simple, but it isn't really simple. In this case, what I'm showing here is if you have a system that has some processors and some local cache, you can expand that capability by stacking a system-level cache die on top of it. In fact, you can also play, in this concept, you could stack more of them and have multiple stacks. The advantage of stacking memory, especially SRAM, on top of a processor is that it doesn't generate more heat, so you only have to solve the heat constraint for the processor part, not for the memory part. SRAM is better than DRAM in that the heat doesn't kill it, and so on. But nonetheless, the details of this we can go into, but the key point really is that the ability to build these vertical structures changes what we can intuitively think about as what a hardware design looks like. There's might be at some point a mix and match capability, but right now it's more like we can extend the memory system into higher dimensions, and that allows us to build different structures than we're used to when we're used to just a single bus rather than zillions of parallel buses. Alternately, we can mix FPGA and ASICs or SoCs together. And here's a couple of examples. So this was a paper that Paul Watmo and friends put together a few years ago from Harvard and ARM. And you can see there's an eFPGA component to that. The rest of it is kind of like stock or standardized SoC with machine learning capability. And then there's this programmable part that you can do other stuff. The Xilinx keynote at ISSCC this year approached a similar look at the problem, where you have this FPGA fabric that you can map to different devices or different algorithms, and then around it you have a bunch of standard programming functions, so CPUs, GPUs, and what have you, IOs, PHYs. And both of these structures allow you to get close to the software-defined hardware vision of, I can put something in that programmable fabric, and then I can change it. If I don't like the way that it's working, if I change my algorithm, I can change the fabric. In theory, you could do that dynamically. In practice, you probably wouldn't. Another thing to look at here is these spatial architectures. So again, this is originally defined, translation of high-level language programs directly into hardware structures. The key features of that is using many simple processing elements arranged into this kind of fabric. It's a data flow computer, effectively. You can unroll the workloads in space. And because the memories are local, you get this kind of scratchpad effect. You can actually tune these things and program them to do some quite significant computations. There was a lot of work on that a few years ago. Recently, with things like Iris, SOTA, or DSA Gen, there's been a lot of renewed interest in these. These, I think, have the capability to implement an interesting part of our software-defined hardware vision. And again, they augment, they don't replace existing processors, which again fits in with our dark silicon mentality. All right, so what's the winning combination? I think we really don't know. First of all, we may never achieve the grand vision of software-defined hardware. It does probably involve solving general AI, but I think we can get close. And we're beyond the era of one size fits all, which means that we have answers potentially to the objections that were raised earlier. So we don't know what we want. Because we don't know what we want, there's really opportunities all over the place. Well, let's see, did we want this? Did we want that? Did we want something else? Can we put them all together? We keep wanting more. That's a good motivation to pursue ideas. And even though what we want might be impossible, it doesn't mean we can't get close. As the Rolling Stones said in more British pop from years ago, you can't always get what you want, but if you try sometime, you'll find you get what you need. So that's it. Thank you. All right, I guess we have time for Q&A, but I'm not quite sure how to see the question.
Yeah, sorry, it was in mute here.
Oh,
so
okay.
Thank you very much for your nice, inspiring talk. So now it's time for questions. So if anybody that has a question, please put it as soon as possible in the chat channel. We have a question by Professor Sérgio Bumpi from our Federal University of Rio Grande do Sul at Porto Alegre. Hi, Rob. It's good to hear you again. What are the features still missing and neither system Verilog on one end and on OpenCL on the other end to provide useful language support for this software-defined hardware vision?
Yeah, that's an excellent question. I think there's two potential answers to it. So the one answer, the simple answer would be that there may be nothing missing from either. That OpenCL may be perfectly fine at what it's doing and System Verilog is perfectly fine at what it's doing. But what we're trying to get is a better mapping between the two. So it's the mapping that we don't understand. That's, I think, the easy answer. The more complicated answer might be that we need to be able to move some of these ideas of parallelism and intent further down into the implementation stack. So there's features inside of System Verilog that allow you to declare arrays of objects. And basically the features are kind of there. But the piece that is challenging is actually implementing those parts. So a lot of times you get this idea of, well, here's the language allows you to do this, but the actual implementation only, or the tools will only work on a subset. There's another important angle, though, which I think gets to this dynamic bit, that implicitly in the way the hardware descriptor languages are run or are defined, they're very much, here's a structure and it just exists. Whereas what we're thinking about is how can we dynamically map between structures? So it's the overlay on top of it that's really important. So there's so I guess I'm not sure that's necessarily the best answer to Sergio's question, but there's a lot of opportunity that exists, and I think it might be too soon to say exactly how these languages need to be modified. I think we need to try a few things and see where the shortcomings are.
Thank you. There is a second question by Sérgio Bumpi. To realize this vision, do you see that eFPGA is definitely technology that needs to have in the platform? Does that explain the gobbling of Altera into Intel and Xilinx into AMD?
I think that's certainly a good explanation for why they might have done that. Yeah, and we've seen published data. So Microsoft, for example, a few years ago said that they had looked at building a customized accelerator for their data center, and they concluded that the actual algorithm that they wanted to accelerate evolved so many times over the production cycle of an ASIC that it was actually far more sensible to just put it on an FPGA, because the FPGA was able to be changed multiple times in a day. So I think there's a need for a programmable fabric, or the challenge that the programmable fabrics have is that we sometimes like to think, oh, the FPGA will just be a tiny little corner of the design. But realistically, because FPGA constructs are significantly less area efficient than standard cells, you wind up with these programmable blocks actually taking large chunks of area. So that may, in fact, be the motivation. I won't claim to understand why Intel or AMD do things, but that may be part of their motivation in gobbling up Altera and Xilinx.
Thank you. There is a question by Fernando Luis Oliveira. So he says, software-defined hardware is in constrained devices. Can you assume that is the opposite? An embedded system imposes situations that we need to refactor the code in order to save resources.
Yeah, that's also a good question. And I think there's a couple of that what Fernando is describing is, I think, the current situation where you have whatever system that you're working with, embedded is kind of the most constrained, but even pretty much any system has some constraints that it's operating under in terms of what its power limits are, what its thermal limits are, and what its physical, memory limit is. How efficient we can make things and how we can squish more into that is kind of what a lot of us are doing all day. Is we have these compute capabilities that we want to squeeze into the hardware. So effectively, I think as the point Fernando was making is, we're kind of doing this hardware-defined software of, I have this piece of hardware, it's only capable of doing X, therefore I need to tweak the software until it fits. And that's kind of where we're at. But I think this vision of, could we change that so that we could build, even for embedded systems, even for things that are operating in exceedingly constrained power environments, could we create a system that's more able to handle a more arbitrary class of program for itself? That's kind of what the motivation is behind this. So again, I think, as I've said in the talk, I don't think we're there yet, but I think it's still a good vision to work towards.
Thank you. There is a question by Professor Claudio Diniz. Thanks for the excellent talk. What is the role of the open source EDA tools to enable a better software-defined hardware?
That's another good question. I think ARM as a company tends to be, we're agnostic on open source versus closed source for EDA, and that as long as somebody solves our design problem, we're happy. And so that's internally, and externally, our customers use pretty much, any variety of EDA that you can think of. So we have to be able to support everybody. But it is a question. I think that the opportunity for open source kinds of EDA flows is really in the ability to rapidly iterate. So if we're looking at something where, again, we go back to, we're not really sure how to solve this problem. If we have an open source tool environment, that means that lots of people can be thinking about it and working on it simultaneously, and they can experiment on different ideas, and eventually in that experimental flow, something will emerge of, oh, this actually seems to work well. And then when that happens, then that either might continue as an open source thing, or it might actually be absorbed into the commercial EDA. And again, at that point, it's what happens to it at that point is more of a market thing. But the benefit of the open source ecosystem up front is that it allows this this vast amount of experimentation without necessarily having to worry about all the productization that would need to be built around the code if and when it eventually became widely deployed.
Okay, thank you. So now a question by Lawrence Laforge. What do you envision as the proper ratio of interconnect to active elements in a software-defined hardware architecture? What is the right cost of hardware fault tolerance?
Yeah, those are also both excellent questions. So on the first one, I think I won't claim to have the definitive answer on what is the actual correct ratio of interconnect to processors, but I think what I will argue is that for a true software-defined hardware implementation, it's going to have to look, at least for some of the processing elements, more heavily weighted to the interconnect. So if you looked at that spatial thing, for example, there's a lot of interconnect in there and a lot of effort that goes into it. That effectively that data flow dominance, I think, is something that's going to be important. Exactly how important and what's the precise number, I don't know. The fault tolerance piece of it, I think, is somewhat orthogonal, but equally important. And the way to look at that, I think, is it goes back to the it just works bit. That we need to make sure that whatever it is that we produce just functions. Now, in existing CMOS-y kinds of technology, we have a pretty good intuition about what level of fault tolerance we need for different applications. And something that runs in a spacecraft or a medical device needs a high level of fault tolerance, but so does something that runs in a data center that's expected to have constant uptime. On the other hand, in a lot of lower cost devices, then it's just perfectly adequate to just shut the thing off and reboot it, because that's what people are used to. But I think as we push the boundaries of Moore's law a little bit, we're going to run into new devices of various kinds. And in those cases, a lot of what we've been looking at in terms of new materials or emerging memories and so on have significantly lower or significantly higher fail rates than we're used to with CMOS. So fault tolerance, I think, is going to emerge in there as well. There's a second aspect that I think Lawrence might have been getting at as well, which is that because in a lot of these applications, ML, for example, is kind of inherently fault tolerant, there may be approaches that we can use to incorporate our uncertainty about what the thing is actually meant to be doing into actual benefits in the computation. So we might be able to exploit error tolerance somehow. Or we might be able to resurrect things like Razor that never quite worked in mainstream CMOS and CPUs, but might work in some of these new kinds of techniques. So yeah, I think there is a lot of opportunity in fault tolerance. I think it's going to be a resurgent research area as we move forward in this area.
Okay. So now a question by Professor Altamiro Suzin. Software is not like hardware. In the 70s, we had hard work to convince people that is not chaotic, such software guys used to say. In what sense it could be? Could it be at the algorithm level?
So what was the last part of the question? I think I missed it.
The last sentence was, could it be at the algorithm level?
Yeah. Yeah, it's an interesting question. That maybe the algorithm level is, I think, clearly part of this solution. And it is going back to the software is not like hardware. And the hardware differs really because it's so expensive. It creates this mindset of we have to have everything right, and then once we have everything right, we'll press the button and make it ship. Whereas the software mindset, it's not quite chaotic as much as let's get it mostly right, and then we'll patch it with we'll patch any minor problems that show up. So I think there's this part of the challenge with the software-defined hardware is to map these two mindsets into something that can coexist. And exactly how to do that, I think, is kind of an open problem, but I think it hinges around the concept of verification, validation. How is it that we can be sure enough that what we want to put into hardware is going to function and be fixable without having to go respin whatever hardware comes out of it? So there's figuring out how to tie the two worlds together is really going to have to involve figuring out a common mindset that can exist at this boundary between the software view of the universe and the hardware view of the universe.
Thank you. So now a question by Jur Vreka from Joseph Stefan Institute in Ljubljana, Slovenia. So thanks for the great talk. A lot more people know how to write software. Do you think there could be an issue that people just keep using just the CPU and not any specialized hardware blocks or FPGA?
There could be, and it wouldn't be the end of the world for ARM if everybody decided to keep using CPUs forever. We would be fine with that. But I think that, and I think the point of the relative number of hardware and software engineers is really important, because it means that the talent pool of it, if we can figure out how to harness the creative capacity of all of the software designers in the world and get them able to exploit hardware, then that's a benefit that will help hardware design. It'll help all of us somehow. And so figuring out part of the challenge in software-defined hardware is to figure out a way to formulate the hardware problem in a way that fits nicely enough into a software ecosystem. And there's various efforts in that around now. Chisel is an example of something like that. How do you frame hardware design in a way that software designers can understand it is a really interesting problem. There's a vague analogy in analog versus digital in hardware design, in that there are far more digital designers than there are analog designers. So rather than have analog design be a complete bottleneck to every chip design, you wind up centralizing on a very limited set of analog functionality, and a lot of that analog design consists of let's digitize whatever this analog thing is as quickly as possible and process it, and then at the end we can put it back into an analog signal somewhere. So there's, I think, a similar thing of how do we do as much processing as we can with some kind of clever software on some smallish set of customized hardware structures. And in that case, even these FPGA fabrics or these spatial fabrics are examples of the kind of structure we could map to. But again, how do we make it so that everybody who wants to write a program in Python doesn't have to learn how to construct a standard cell library? It is a useful goal.
Thank you. So now we have a question by Abe Elfadel from Khalifa University, United Arab Emirates. By the way, Abe will give a talk to us on June 11th. So he's saying, hi, Rob.
Hello.
Great to see you again. Great talk. What is the deal with the virtual prototyping, and how does it relate to software-defined hardware? Are they two sides of the same coin?
Yeah, I didn't mention that in the talk, but I agree. They are kind of two sides of the same coin. That there's that part of the ability of having of creating this pathway that says I have a bunch of software and I want to make hardware go, or I want to make some hardware of it. The ability to do virtual prototyping, the ability to try out different things in some sort of either virtual or simulation-based environment before you commit to making them in hardware is absolutely critical. So yeah, I agree. They really are two sides of the same coin.
Thank you. So now I have a question from myself. So, well, we are seeing nowadays, everybody can see that power consumption is more and more a major issue. There is a prediction that was published, I think, 5 years ago, saying by the year 2040, if there is no major change in the design of computer systems and chips, to run all the computing electronic system will need all the energy that will be produced in the world in 2040. So to try to optimize the systems, what do you think about the use of architectures based on hardware accelerators? As you can see nowadays, there is several system on chips that have a large set of hardware accelerators. But what about an architecture based only with hardware accelerator with just a CPU to manage the system?
Yeah, that's a good question. I think there's several pieces to the answer. The first one is that whenever you see a prediction that says that something or other is going to use up all the world's energy by some date, then you know that something will change before then, because that will never happen. But instead, we can look at what might happen instead. And I think the dark silicon exercise gives us some insight there, in that if you took a scaled chip, or if you took a 7 nanometer chip and you built up a reasonable sized object that was, a couple of centimeters on the side and had everything running full blast all the time, this thing would literally be consuming hundreds of watts. And that just really, the number of applications where that's possible is very small. So instead, what you look at is what you can do to optimize what you can do to put on different accelerators and different functionality, as you said, and sort of turn them on and off when you need them. And part of the SDH, or software-defined hardware thing, is how do we choose that wisely? There's just a related emphasis, though, which is that even if we do all that stuff as we've described, we're still going to wind up with things, if we're going to try to use or take advantage of machine learning capabilities, I think we need to figure out how we're going to solve these massively larger problems. Part of that is going to be continuing to make the things that solve those problems massively more energy efficient. And in some ways that can be done in the background, in the same way that somebody can optimize a Python library behind the scenes and you don't really notice it until you update it. We can optimize the hardware to an extremely great extent and have that be effectively transparent from the people using the systems. And I think that, again, is part of what we're going to have to do. But I think that layered on, the final piece, I guess, layered on top of that is that we're going to have to figure out, for an energy sustainable future, just how we're going to deal with the energy that our computations are consuming. And figuring out where those trade-offs lie, I think, is part of the both technical and ethical responsibility that we have as engineers. Is, do we really need trillion parameter models? And if we do, how do we develop them? How do we create such things more efficiently than we do now? How do we deploy them more efficiently than we do now? How do we make sure that the problems that they're solving are decreasing the world's net energy consumption rather than increasing it. And that I think, again, over the next 20 years, all that stuff is really going to be important.
Thank you. So another last question is, so we can observe nowadays that some very nice systems and that they are using much more transistor than is needed. So it appears that in some cases there is a lack of optimization at lower level. And what is your consideration about this?
Yeah, and I think that's, I think that actually has an opportunity to get better. And I think it kind of boils down to this Moore's Law cadence, that in the era where everything was changing and the process was doubling in its capabilities every 18 months, the most important thing in design was to get it done now before somebody else got their design out the door and theirs ran faster than yours just because they happened to target a slightly later version of the Moore process. In an era where the processing is not advancing as quickly, where the fundamental electronics isn't going as fast, that means that there's more opportunities to optimize the design, and that those also coexist with the energy and thermal needs that you get. So as I mentioned, if you took a 7 nanometer or a 5 nanometer chip and you ran it full tilt, it would be consuming hundreds of watts. If you optimize the hardware, maybe it wouldn't be. And there again, there are commercial existence proofs of people who've done kind of fundamental rethinks of how their silicon was working, and they've been able to achieve some very significant power gains by doing so. So I think that, again, there's lots of opportunities like that out there in terms of hardware optimization. And again, from a software-defined hardware view, the idea is that all of that stuff, or not all of it, but to the greatest extent possible, that those hardware optimizations would lie under the covers, and that behind the scenes from the software engineers' perspectives, they would just be doing things and that magically they would become more efficient. On the software side, more efficient in coding and more efficient languages and so on, I think is, again, an important research topic. But the ongoing need for energy optimization of all kinds and on all levels, I think, is really important.
Thank you very much. So there is here several congratulations for your very nice talk. The last one is by Professor Bumpy, that I think represented the opinion of everybody that is attending your talk. So thank you, Rob, for sharing this vision with our chapter in South of Brazil and friends all over the world. And today it was possible to identify by the ones that identified themselves by the chat channel, that we had attendees from Canada, USA, Italy, UK, Portugal, United Arab Emirates, Germany, Chile, Peru, France, and Slovenia, and Brazil. So, but there is still another question by Professor Surzin. Machine learning is the challenge nowadays. People say that we need, in fact, machines that learn to learn, or general machine learning. Do you think it will be an evolution or a new structure of architecture?
That's another good question. I'm guessing that it will be a different structure than what we have now, because I don't think we have achieved everything that can be achieved with neural net structures, but we've already seen that various evolutionary changes to them are making them more and more suitable for different classes of problems. But effectively, we have a kind of understanding of how to solve vision problems, how to solve natural language problems. But I still think we have work to do on kind of the next layer up in intelligence in terms of perception and meaning and that kind of thing. And I suspect that will involve different structures. It may just be that I'm not creative enough and we can do it with the existing ones. But yeah, I would bet on them being beyond what we have now.
So thank you very much again, Rob. And I hope to see you in person in a near future. And
Likewise.
at least at DAC in December. No?
Yep.
So thank you. Bye-bye to all the attendees. Thank you to attend this talk today. Bye-bye. Have a nice weekend.